Although this next set of computations, which comprise a stepwise approach to solving this problem, are not set up in this interactive clickable style, they illustrate a pedagogical approach which I think is effective based on the experience that I had using Maple in the classroom at Rose-Hulman. This is the differential equation. This is the set of initial conditions, and here is Maple giving us the analytic solution and drawing a graph of the solution. Now, back when I taught at Rose, this new interface did not exist, and I had to teach students the various commands for them to be able to do the equivalent of this. But what this illustrates is a synopsis, glimpse of the approach. State the problem, get Maple's solution as expeditiously as possible, draw the graph, and talk about the problem and what the solution tells you about the problem. All the details that might require computation, use Maple to do that, but just make the problem and the solution clear to the student. After that's done, then begin the process of implementing the solution algorithm, but use Maple to implement the solution algorithm, and that's what I'll do next. And I've got this set up in a command style so that we can get through this more efficiently. So here's the differential equations fundamental set. Maple can provide that by simply asking for it. And then you ask, well, where did that come from? Well, you make the exponential guess, which means you take e to the lambda t, you plug that into the homogeneous equation, divide out the e to the lambda t, and you have the characteristic equation. You solve the characteristic equation for the characteristic roots, and you place the characteristic roots up into the exponential where lambda was, and now you have two complex solutions. Now we're supposed to be figuring out where this pair of solutions in the fundamental set came from. Well, we now have these two complex solutions. Take linear combinations, because by superposition, linear combinations of solutions will be solutions. So we add and divide by 2, we subtract and divide by 2i. We now have the fundamental set that Maple created. Now we need a particular solution. You can ask Maple for a particular solution. And then you ask, where did that come from? How did you get it? You have two methods. You can use variation of parameters or undetermined coefficients. Let's use undetermined coefficients, which means that you need to write a template with parameters a and b. How do you determine the a and b? You plug this into the differential equation, and you choose a and b so that the result is an identity in t. Okay, Maple has the ability to solve for a and b that make this an identity. Well, if you don't have such power available, you go back to the way I learned how to do this more than 50 years ago when I was in college. You collect like terms and you match the coefficients. If you do that, you generate these two equations, which you then solve for a and b. Notice you have the same a and b. Therefore, we can declare this to be the particular solution. Well, we have the particular solution. We can now write the general solution. That introduces two more arbitrary constants. They're determined by the initial data. Now, these two equations are a result of applying the initial data, and all of this coding here just means that I can hit the enter key and it will reach up and grab the information where it was listed at the beginning, and I don't have to go up and down and type numbers in. We solve these two equations for A and B and insert those values into our general solution, and then compare to the solution that Maple gave. They agree. If they didn't agree, we would have to find out why. Were they different, really? Or were they just in different form and are essentially equivalent? This is the kind of work that I would have my students do as homework in this style. Solve the equation, get the solution via Maple, and ask some interesting questions about the solution. At what time does the solution fall within a given band of the steady state, etc. Then I would have solve the problem stepwise using Maple to implement the steps of the algorithm. And they needed to practice this several times in order to get the structure of the calculation clear in their minds and see where all these details fit in. Then, when it becomes clear in a big picture sense, if there are some skills that you insist that the students have manually, you'll find that they will acquire those skills more readily. First, because they've seen what the particular skill looks like, and they've also seen what the result is and where it fits into the overall picture. I found this to be an effective, efficient way to use a tool like Maple in the classroom.